Does
Okay,
that
perfect. Oh, it
whoops.
was there for a second.
Yeah. Okay, that work?
Okay. Yep, there you go. Yeah, you're very punctual, which I guess makes sense for someone who studies clocks for a long time.
Well, I'm not very good at computers, I must say.
All right. So first question, how does one laser cool something? Like I have a laser engraver in my garage and it seems to only burn things. Um, how did like it seems intuitively backwards. How do you do it?
Yeah, so there's just a couple of simple ideas that come into it. So basically that, you know, atoms, for optical transitions, they tend to absorb at one particular frequency. And be some spread, due to the line width. But and so the other ingredient, when if the atom is say moving against a laser beam, there'll be a Doppler shift of the frequency. And so the idea of cooling is then that you tune the laser below the frequency where the atom wants to absorb when it's at rest. And then so when it's moving against the laser, it shifts the frequency up. And so then it'll scatter when it's moving against the laser. When it's moving away from the laser, it's shifted farther away. So there's this big differential in whether the scattering when the scattering occurs against moving against the laser beam versus when it's moving away from the beam. And that's it.
That's really cool. Almost like it's only visible when the situation would be such that it would lose energy in the collision.
That's well the cooling. That's right. And
Yeah,
opposite effect. If you tune above, it'll heat. So
interesting. That's
yeah.
cool. So another non-intuitive phenomenon that you're probably familiar with is Earnshaw's law or Earnshaw's theorem, which says you can't create a stable equilibrium with
Right.
static electric fields. How do you get ions to kind of levitate in the same place?
Yeah. So the idea is, again, it's fairly simple that you use an inhomogeneous electric field, and so that the when the basically and so the idea is that when the atom is moving against the electric field, it feels a force, and it moves away from the electric field. It feels a smaller force. And so the idea, though, is that you can make if you make a standing wave, then that if the atom sits at a node, of course, it doesn't feel any force. But if it moves away from that node, it'll feel an average force, and that's it. An average force when you average over the oscillating potential.
That makes sense. So your Prize in Physics was awarded kind of for the application of these non-intuitive phenomena. Do you have any thoughts about this year's Nobel Prize in Physics? I believe it was like macro scale quantum phenomena.
Yeah, these are the guys that actually I know two of the guys that received it. In fact, John Martinez, one of the guys he was one of my colleagues at NIST when I was there. So anyway, they're working on superconducting circuits to make qubits, and but so I mean, it's a very strong technology. It's not, they may be the ultimate winners for a quantum computer. They're certainly a strong contender, so we'll see. But anyway, so I think that's the Nobel Prizes this year in part recognize their achievements. I think towards you know quantum computing and things like that.
Yeah. So your graduate professor was Norman Ramsey,
Right.
himself a Nobel Prize winner. By the way, I went down a Wikipedia rabbit hole and I found that like so your advisor was Ramsey, his advisor was Ising or Rabi, sorry. Um, and then if you keep going up 12 advisors, like back to like the 1500s, you end with Friedrich Leibniz, like the co-inventor
Yeah.
of calculus, which I thought
Yeah, I
was kind
think
of
you
cool.
had mentioned that in one of your emails. Yeah, that's amazing. Yeah.
Yeah, it was
Uh,
crazy. Um, is there anything that you learned working for Ramsey that you still think about or use in your research?
Well, I mean, he was, I don't know, I mean, he, first of all, is a very, very nice person, easy to work with. And so, but he just, he basically, his main thing was just be careful, when you're, when you're analyzing some problem. And in fact, it's interesting though, the story was when I was a graduate student with him in the late 60s and 65 to 70 basically. But anyway, at that time he was heavily involved with Fermilab setting it up. And so he was gone most of the time. So in fact, I mean, there was a group the group was about 8 graduate students, and we just learned how to help each other.
Nice.
Ramsey would didn't really interact directly at all. I mean, we'd have sort of semi-weekly meetings, where we'd explain what we were doing, and he was always, careful about, tending there and offering advice. But
When you
he didn't.
say, sorry, go ahead.
Oh, I was just gonna say he didn't really come down to the lab.
When you say careful when doing research, do you mean like be careful not to fall for false positives, or be careful as in like just being like, I guess, methodical about
Yeah,
all
I
your
think it's just
components?
being, yeah, methodical and, finding different ways to check yourself that sort of, nothing profound, but I think, I think he exemplified that, so.
Did you find that any of your machines ever had like an attitude or personality, or like you have to do something unexpected to get them to work?
No, not really. When they weren't working, I mean, you had to search around, but there weren't any, didn't hit it with a hammer or anything.
Sure, yeah.
It was always, in
It
the end, it was pretty simple explanations for what was wrong if it wasn't working. So, no real magic there, I would say.
it sounds like just regular research, like just look at what the problem is, and then hypothesize about what the issues could be, and then just methodically go through each one at a time and
Sure,
sort them out.
sure. Yeah, that's right. Nothing, nothing profound there. Yeah, that's right.
Makes sense. So uh, I find it kind of crazy that it's almost like you have to be an expert in both like particles and electronics and like creating the fields, and also setting up your lasers correctly and dealing with all of that and the timings. Um, and as an experimentalist, I find it hard. Like the hard part isn't getting all the individual components to work, but um, getting them to work together. And so kind of like the last question. Do you have like a ritual or like a way to get, what you check when you have that last bit of noise in your measurements, and like is there something that you look to try to get, the noise down?
Well, well, I don't think there's any set formula. Obviously, just, yeah, I can only state the obvious, and that is you're trying to search for noise sources and look in the obvious places where there might be noise. For, the electronics are certainly in the laser, that sort of thing. So, uh, yeah, I would say no magic. You just got to search around and, try to find where the problems might be.
Um, where do you normally have issues with the laser? Like when you're setting up lasers, what usually causes the problem for you, if there is a problem?
Oh, I mean, I don't know if there's any given thing. I mean, there may be, you know, most of the lasers we've made are, pumped by other lasers, so you have to worry about the pump lasers, if they're working properly and so on. But and of course, whether in a laser, whether the mirrors are aligned, things like that. So I mean, there's nothing really, fancy about what we do there to try to check why if things aren't working, But
That makes sense. So I don't know if you knew this, like the atomic clocks have gotten pretty cheap these days. I found a rubidium standard for $150 on eBay the other day.
uh-huh.
It was used, but and I have this dream of making an atomic wristwatch out of one of those. I was wondering if you had any advice for that.
Well, you know, I I would say, well, first of all, I mean, usually any sort of atomic clock has got some enough ancillary equipment on. It's hard to mounted into a wristwatch. And but just as a practical matter, our iPhones, do a pretty good job of tracking time, and so at least on the practical scale, that works just fine. So we don't. I'm not. I'm not sure. eh, You know, I don't want to discourage you about your atomic wristwatch, but I think it'll be hard to economically replace an iPhone, getting signals from GPS or something like that.
That makes sense. Do you have any possible applications? I mean, other than looking really cool, do you have any applications or like, maybe demonstrating Einstein's relativity on like airplane flights that you can think of for something like this?
Well, I mean, actually, you may know that one of the first tests of the time dilation shift was with clocks was a guy, Hewlett Packard, he took a plane on an airplane, a cesium clock, a portable cesium clock on an airplane, and could compare it to one on the ground, and they could see the shift anyway, due to the relativistic shift. It was a small effect, but that was just kind of a nice demonstration experiment. But of course, the experiments now are much more precise, and at least we can compare different clocks in the lab, and get very good comparisons that way.
Yeah, I was at the Quantum Symposium in Fermilab last week, and one of the talks was talking about optical clocks in the like optical atomic clocks, um, like being able to differentiate the relativistic effect like millimeters apart from each other,
Yeah,
basically proving the
and
relativistic shifts.
who was the speaker? I may know who the speaker. Chun Yi,
Ooh.
does that ring a bell?
Hold on, yes, yeah, no, yes, it was him. Yeah, he was giving a keynote. That's correct. Yeah.
Yeah. So anyway, he kind of holds the record now on being able to sense small relativistic shifts, over some millimeter sizes and things like that. So he's got the best experiment for that right now.
Um, yeah.
You may remember he's actually measuring it's a optical transition about 150 nanometers, but it's actually a nuclear transition that he uses anyway. So it can be very precise. So that's really an impressive experiment, I think.
What I liked about his talk is he explained how like the amount of energy difference between two states is very small, but
All right.
how the energy gets there is like, like 10 orders of magnitude bigger of what the so basically there's an interplay between the Coulomb forces and like the nuclear forces, and the amount of change in energy is like 10 times bigger than what's actually emitted in the nuclear clock, but it's just interchanging between, going basically between the Coulomb and the nuclear force. And it's almost like the nucleus has like two metastable states, and it's kind of going between the two.
Right. Yeah, I'm not sure what the point there was, but anyway, that's right. Yeah.
Um, can you think of other example or other potential uses for this kind of technology, like being able to probe relativistic shifts over that small of an area?
Say again, what was your last sentence?
What potential uses, like gravitational mapping,
Oh,
dark
I see.
matter,
Sure.
timekeeping?
Well, there's certainly, atomic clocks are used to measure the geoid around the Earth, for example, and so that's a common use, to measure the gravitational shifts around on the surface of the Earth, looking for anomalies, say, for example, you could, if there was a pocket of lead somewhere, should be able to detect it underneath the ground using an atomic clock, that sort of thing. I mean, it
Like,
hasn't really found a practical use that way, but that's one gee whiz kind of example.
yeah, like prospecting. That actually makes a lot of sense. It'd be cool if someone did that. It reminds me of people using muons to find the vacancies or the holes in the pyramids.
Uh-huh. Yeah. Yeah. So,
So sorry, you're gonna say
oh, I
something.
was going to say one of the attractive things for people with clocks these days is looking for dark matter. And so, we'll see what happens there. But in principle, they could be, sensitive tests of dark matter. We'll see about that. But
So there's a lot of trapped ion research directions that are pretty exciting these days. Um, which ones do you find like worth your time being in the lab, and which ones do you like leave to others? Or a better way to put it is what do you find keeps you busy research wise? I mean, obviously ion stuff, but like what particular ion stuff?
yeah, well, I think, that realistically, I mean, our group is fluctuates a bit. That's about 8 people now, and it doesn't. I would say it doesn't me going in and tweaking the knobs is probably not the best use of my time because I'll get called away or something, and then that disturbs the flow of the experiment. So I more go in and kibitz with people, and what's going on, and try to, you know, problem shoot that sort of thing. And of course we have regular weekly meetings where we discuss the issues going on, and so that helps a lot.
What would you say is the hard walls these days for trapped ion quantum computing? Heating, crosstalk, mode crowding, laser complexity.
Yes, all of the above. No, I mean, yeah, I mean, we have to worry about all those things. And I think, it isn't, you know, I would say, I think we can say ions are a contender. That may not be the ultimate winner, but I'd say, there's a lot of positive, feelings about, and superconductors too are I'd say that's the main competition, and it may be that may really take over in the future. But at this point, I think, the ions still are a contender in this business. We'll see.
You have any thought about the other two, neutral atoms or photonics?
Well, yeah, neutral atoms is, be very much the same. The issues are very much the same with ions. There's obviously different technical problems. And I think, in terms of photonics, I think I'm not the expert to say, but I think it's just harder to hold photons in one place for a long time, So I think
Yeah.
that's the big technical problem. But still, it's a very viable, platform. But I'd say that's the main problem. The nice thing about atoms and ions is we make a qubit, it can stay, keep good shape for quite a while on some interesting time scale anyway. Yeah.
Yeah, Jun Yi, I think I'm probably mispronouncing his name, but yeah, he was talking about how he had like something like either seconds or minutes of coherence on his particles, which is yeah,
Yeah,
insane with when you think
yeah,
about their frequencies.
yeah, yeah. Well, I mean, yeah, I mean, that's especially relevant, because he's at such high frequency for lower frequency clocks. I mean, they can be coherent for hours,
Yeah.
but anyway, but no, certainly what he's doing is, really impressive, I'd say. And you say his name is, he pronounces Jun,
Jun
Junye,
Jun
Jun,
Yi. Okay.
Jun, kind of like June, but
Jun.
anyway.
Cool. Good to know. So speaking of coherence, um, you've been doing this for a while now. How would you say your thoughts about measurement and decoherence have evolved over time? And is there a question that you wish people would ask or that you think people should be asking differently?
Maybe I don't quite understand the gist of your question, but I don't think I don't have any profound thoughts on that. Obviously, we're trying to make things coherent as long as we possibly can. Depends on the system, but also relatively speaking, for example, for clocks, what's relevant is the coherence time, but also the frequency that you're operating with. So you want a very high frequency and long coherence times in general for clocks. And so, you can win both ways, high frequency and, long coherence. So, but, I would say there's no magic formula for, saying how that guides you to the particular a particular clock, for example.
It sounds like just over time, you've just basically just seen things get better and better. The coherence times get longer, the frequencies get higher, that
Yeah,
kind of
that's right.
thing.
Yeah, for sure. Yeah.
Makes sense. So a bit of a personal question. So I am envious of your mustache. I know lots of my viewers are. I don't have the ability to grow a mustache, mostly because my facial hair, like the coloring, is just weird compared to the rest of my hair. Anyways, does your mustache have an origin story?
Oh, I don't know. I was an undergrad at Berkeley in the 60s, when the hippie stuff started. And so that's when started growing my first mustache, just to kind of fit into that crowd. But
That
other
makes
than
sense.
that, no, no, nothing real special.
And the last question is there anyone that from your past that you miss working with?
Well, I'd say there's several people. Certainly, I mean, I've always been in a group situation for, uh, doing these experiments. And so I mean, you know, for example, most of my career was at NIST, and I mean, I had good relations with a lot of people. There's one person in particular. His name is Jim Berquist, and he was a laser expert, and he, 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 for example, made one of the first high precision optical clocks using mercury ions. But anyway, we just, personally hit it off. We liked working together in the lab, but also we like outdoor activities. We played on a volleyball team, and we got into, long distance bicycling on the weekends, that sort of thing. So, we just always had a good friendship with him, and still keep up with him. So.
Nice. Kind of sort of follow-up question. You mentioned working in groups a couple times. What is it about the groups that you really like? Is it that, everyone can just kind of talk about and share the same problem? Is it the specialization where like you can just let someone else do the hard part that, they find easy and vice versa? Or what draws you to groups?
Well, I think yeah, it's a mixture of both those things. I think, yeah, I mean, certain people are going to be better at, you know, lasers or computers, and so people you know tend to concentrate on different people tend to concentrate to different aspects of the experiment. But uh, I mean, the other thing is, I think is, what's nice is just in a group situation, you can always be troubleshooting together. You're not stuck wondering by yourself what's going on. And so, a group discussion always ensues when, we got some problem with the experiment. So that part is really nice about working with a group. And anyway, it was just a good, friendly experience, I would say, that, working in a group.
And succeeding together?
Yeah, yeah, for sure.
Cool. Well, Dr. Wineland, thank you so much for taking the time to talk to us. It's been a pleasure. Oh, great. Thank you.
Yeah, you're welcome. Nice to talk to you. Yeah.
Nice to talk to you too.